we're still going to have to continue verifying. You're just going to have more formulas to choose from to verify. So the cosine of 3 theta equals 4 times the cosine cubed theta minus 3 cosine theta. What do you think you could do? Does anyone see any move that you think you might be able to make to either side? If you just had to blindly start and do something to some side, what could you do? Stephen? Jalen? Right, you could factor on the right, factor out a cosine theta. Okay. Let's do that. We'll take a cosine theta out, and then 4 cosine squared theta minus 3. And that's really it on the right-hand side. I don't see anything else that you could do. The cosine 3 theta, and I think I'm going to open your eyes to something new to add to your bag of tricks, is we could separate this into cosine and change the 3 theta to 2 theta plus theta. And in doing that, we've made this the cosine of a sum. So we can go and use our sum and difference formulas. Cosine of something plus something is cosine cosine minus sine sine. So I can split this up now using my sum of cosines formula. So that's cosine 2 theta, cosine theta. What did I say? Cosine cosine minus sine sine. Minus the sine of 2 theta, sine of theta. That's my left-hand side. Using the sum formula to split that up. Now, what can I do to the left side? Say it again. What do you mean? I just use the sum and difference formula. I just use this second sum formula to go here. I don't think I can do that on the other side. I'm not taking the cosine of a sum, or, right? Am I taking the cosine of something plus something, or am I taking the cosine of, what did you say? I'm not, right, are you talking about this subtraction? But it would have to be the cosine of something minus something, and that's not what's happening here. Okay? But on the left side, what other formulas can I put to work here? Stephen? Correct. Are all of your formula sheets out? If they're not out, get them out. You will not find much success doing any of this chapter without that formula sheet as your right-hand man. I regret that I even had to say that. That I had to instruct you to get it out. Now are we good? So, Stephen, what were you saying? Yeah, you can use your double angle formula not just on the cosine 2 theta, but also on the sine 2 theta. Now, on the sine 2 theta, we don't have an option. There's only one formula for the sine of 2 theta. So I'm going to replace that with minus 2 sine theta cosine theta times the sine theta that was already there. But on the cosine 2 theta, I do have an option. And sometimes it doesn't matter. You should be able to find success no matter which one you choose. But one may be easier than another. Any thoughts as to which one you might want to try to use and why for cosine of 2 theta? Jalen? Okay, so that's always a good measure of trying to get some direction, is look at where you're trying to go. Your entire right-hand side is all cosines. So maybe we want to keep this all cosines as much as we can. I think it's a good idea. That's probably the one I would go with. So I'm going to replace that with 2 cosine squared theta minus 1 times the cosine theta that was there. Okay, so I'm going to circle what I subbed out. So on this first one that has a binomial, I'll distribute. I get 2 cosine cubed theta minus cosine theta. That's after distributing my cosine. On the second part of this, my sine theta times sine theta can just become sine squared. Minus 2 sine squared theta cosine theta. And then from the 3 terms here, what do you think? What can I do? Factor out a cosine. So if I take out a cosine theta, I'm left with 2 cosine squared minus 1 minus 2 sine squared. What do you think of that? Say it one more time. What do we make of this? Taylor. One minus 2 sine squared here. 1 minus 2 sine squared is the same as the cosine of 2 theta. So if she goes back here, oops, I should do this. Here's the problem though. Is it a problem? We don't have notes. We're starting on our notes from yesterday. That's not a 1 minus 2 sine squared. It's a minus 1 minus 2 sine squared. You see that? And I can't just like put that in parentheses because technically that would mean the negative would have been distributed. I wonder if we shouldn't have gone this way. Unless someone, I'm sure we could finagle something out of this. It shouldn't be this hard. I wonder if we should have used something else. So maybe we should go back and try to use a different version of cosine of 2 theta. Unless, Stephen, what do you say? I'll give you one more shot. Okay, there we can. So that one we can. Taylor was trying to use this one, and I see why, and I kind of showed you why hers didn't work, but this we can try. So 2 cosine squared theta minus 1 right here is just the cosine of 2 theta. So let's try it. We're kind of going backwards, yeah. What if we used, instead of this now, what if we used our sine squared one now? Would that be helpful? 1 minus 2 sine squared theta minus another 2 sine squared theta would be 1 minus 4 sine squared theta. Does that seem like it would be helpful? Or maybe we use this one. Cosine squared theta minus sine squared theta minus 2 sine squared theta would be minus 3 sine squared theta. What do you think? I did this one yesterday. I did it a totally different way. Let's look at this. I started the same, 2 theta plus theta, and then I split it up. And then I did use a double angle, and I did use that one. I then distributed 2 cosine cubed minus cosine theta minus 2 sine squared theta. So up until here, it's the same thing, right? Good? So then I did 2 cosine cubed theta minus cosine theta, and then okay, so I substituted this with a Pythagorean identity. And so my thought process was my entire right-hand side is all in terms of cosine. So let's get rid of that sine squared. Do you see? So on what we did today, I'm in trouble here. I kind of get to this dead end. The thought process was back in this step. My right-hand side, where I'm trying to go, is all in terms of cosine. So let's get rid of this. 2 cosine cubed theta minus cosine theta stays, but I'm replacing the sine squared theta with 1 minus cosine squared. And then I can distribute the minus 2 cosine theta to this set of parentheses. Are we good with that? I could rewrite this cosine in front of the set of parentheses to make that clear, but for the saving of space, I'm just going to distribute negative 2 cosine theta to the 1 and to the cosine squared. So that's the 2 cosine cubed theta stays, minus cosine theta stays, and then I'm distributing my negative 2 cosine theta to the 1 and my negative 2 cosine theta to the negative cosine squared, which is going to turn into plus 2 cosine cubed. And then I'm just going to combine like terms. So I have 2 cosine cubes and 2 cosine cubes, which makes 4 cosine cubes. And then a minus cosine theta minus a 2 cosine theta, which is going to be minus a 3 cosine theta. And then I'm going to undo the fact that I factored that side. What's that? No, you can simplify both. I think ideally when you start with simple examples, you really only want to work on one side. Because if you work, and the reason is if you work on the left side and on the right side at the same time, you've got too many moving parts. So I like to just simplify one side till exhaustion. And if I haven't reached some epiphany by that point, then leave the left side alone and then work on the right side. And then at some point, hopefully, you see a connection between the two and you can finish off your proof. But you can work on both sides. Never would I recommend doing it at the same time, because that's just too many moving parts. But are we good here? So the right-hand side, I just bring down 4 cosine cubed theta minus 3 cosine theta. Now, given that I had factored the right-hand side, I could have then factored my left-hand side just one more step, and then they would have matched. Either way is fine. Good? So what Jalen said about substituting the cosine 2 theta with this version was smart, because we are trying to get all cosines on the other side. But then realizing that I have this sine squared in there, and trying to get all cosines, again, subbing that out with the Pythagorean identity. Had I continued with the way we started, eventually I could have worked something out. It would have eventually worked. It just would have not been as simple. It would have taken a lot more trial and error. So if I get rid of my sine squareds earlier, I'm thinking if I used one of my sine squared ones for this guy, eventually the sine squared that I use over here would have simplified with that one over there, and it would have taken care of itself. Maybe not. Maybe I still would have had to substitute out taken out my sine squared with the 1 minus cosine squared later on. Probably would have worked. But again, it's a lot of trial and error with these. Any questions? Okay. Exercise 2 here is where we're going to use our power reducing. So write an equivalent expression for cosine to the 4th power of x that does not contain powers of trig functions greater than 1. So I can't have any cosine squareds, any sine squareds in my final answer. That's what they mean by saying does not contain powers of trig functions greater than 1. So if you look at your power reducing formulas, these are used to get rid of squareds on tangents, squareds on cosines, squareds on sines. So they're used to get rid of squared. So the first thing I think I'll do is I'll rewrite this as cosine squared x squared. And then I'll get rid of my cosine squared using this power reducing formula. So just the innermost squared first. So that's going to become 1/2, taking it right off my formula sheet, 1 plus the cosine of 2 theta. That's the whole thing. You got parentheses within parentheses within parentheses here. That closes the 2 theta. This one's going to close the 1 plus. This one's going to close the whole thing, and it's all squared still. So on this innermost side, I can distribute the 1/2. So I'll make it 1/2 plus 1/2 cosine of 2 theta. Nope, I still, technically that cosine is being squared. So I still have to work that out. So I am going to square this now binomial by expanding it. And I'll FOIL it out. So 1/2 times 1/2 is 1/4. Then I'm going to have 1/4 cosine of 2 theta on my outer and 1/4 a cosine 2 theta on my inner. What's 1/4 plus 1/4? 1/2 cosine of 2 theta. And then my last times my last is going to be 1/4 cosine squared of 2 theta. And then I can just power reduce on this one. But be careful on this power reducing because it's a 2 theta. It's the cosine squared of a 2 theta. Your formula is written for a theta. So our quote-unquote theta in this case is a 2 theta. So when I go to apply this formula, getting rid of the cosine squared, I'll just keep the 1/4. I'm replacing this cosine squared with 1/2, parenthesis, 1 plus the cosine of 2, and the theta from my problem is a 2 theta. Are you with me there? So it's 2 times 2 theta, because that's what my theta is in this problem. Let me zoom in on that. Just going to cover that up. So that all really is 1/8, 1/4 times 1/2, parentheses 1 plus the cosine of 4 theta. And then with everything that came before that, which was the 1/4 plus the 1/2 cosine 2 theta. And now it's rewritten without any exponent. Okay? Just for the sake of variety and showing you how there's different ways of going about these problems, this is the way I did it yesterday, which I think took longer. So rather than rewriting it as cosine squared squared, I actually did it out yesterday. I did cosine squared x times cosine squared x. And then I use the power reducing on this one, and I use the power reducing on that one separately. And then I kept this big one in I distributed the 1/2 here on that one, times, distributed the 1/2 there on this one, and then I FOILed. So I did 1/2 times 1/2, and then kind of brought us to a similar place here. And then I had to reduce my cosine squared, similar to what we just did as our final step on the last one. Gosh. But if you multiply it out, let me see how our final answer is. If you multiplied it out and simplified it, that's a power greater than 1. So like, look at how our final answer, I get what you're saying, but look how our final answer is. When we just multiply out and distribute this whole thing out, we have no more powers greater than 1. So by simplifying, I'm saying do all the multiplication out, such that you have no more powers greater than 1. All of our yes, I could reinsert, but I wouldn't want to do that because I can't write it with a power of 2. So there would be no purpose. That would be going against what they're asking me to do. So why would you do that? That's not simplifying. Simplifying is multiplying and combining like terms. That's simplifying. Substituting this out with something else is not considered simplifying. That's manipulating. But I would never want to manipulate and reinsert squares. I know, you're just playing the devil's advocate. It's a good discussion. But simplifying means multiply out and combine like terms. And actually, so I guess to kind of go one more step to listen to my own advice, I should distribute the 1/8. So plus 1/8 plus 1/8 cosine of 4 theta. And then what can I combine? 1/4 and 1/8, yes? That's 2/8 plus 1/8 is 3/8. So that is simplified without any powers greater than 1. Just writing it as cosine times cosine times cosine times cosine is not simplified because you can do that multiplication. Okie doke? Alright. The good news is power reducing shows up the least. FYI. Alright. Finding an exact value of cosine of 112.5. So you sort of saw me do this yesterday on that front example when I was forcing the half angle formula here when in hindsight we realized we shouldn't have. But I don't know the tangent of 15, so I changed it to 30 over 2. I don't know the cosine of 112.5, but I can change 112.5 to what over 2? What divided by 2 gives us 112.5? 225. Because I will know, if theta is 225, I will know the exact value of 225. Because 225 is in what quadrant? With what reference angle? 45. And I do know the cosines of 45. So, from our formula sheet, our half angle formulas are here. And we talked about this yesterday. Plus or minus. You have to decide that on your own based on what we're taking the cosine of at the end of the day. And at the end of the day here, we're taking the cosine of 112.5. What quadrant is that angle in? 2. So should cosine be positive or negative there? Negative. So our answer is negative something. So when we go to apply this formula from the reference sheet, we're going to use the negative when it comes to plus or minus. So we're going to choose to use the negative. And then, God, I wish I could get these all on the same sheet. There we go. Success. So I chose the negative based on the quadrant that the angle is in. Square root 1 plus cosine of, now theta is the numerator now from when I'm dividing by 2. So what is my theta? 225 over 2. And that's what I'm going to now simplify. So, what is the cosine of 225? So, again, back to our question, the reference angle is a 45, so the cosine of 45 is root 2 over 2. 225 is in the third quadrant, so the cosine of that number should be negative. So 1 plus negative root 2 over 2, or you can do 1 minus. And that whole fraction is under the radical. We have to clear complex fractions. So if I look at my fractions within this fraction, my only denominator is 2. So I'm going to multiply the top by 2 and the bottom by 2 to clear. I don't know what that noise is. In my numerator, I distribute, so the 2 times 1 gives me 2. And on my second term, the denominator 2 is going to cancel with that, leaving you with just minus radical 2 all over 4. And then when you take the square root of a fraction, this is all algebra stuff, you take the square root of a numerator, separate from the square root of the denominator. And what is the square root of the denominator? 2. So that is as exact as we're going to get. So, for lack of a better term, I don't even know if this is truly called this, but I think you'll know what I mean when I say it. Our final answer has a complex radical in it. Do you see it? Meaning a radical within a radical. That's okay. Complex fractions, not okay. We know how to get rid of those, but complex radicals are fine. So if we check this, make sure our mode is in degrees, the cosine of 112.5, our calculator says, is that decimal. We got this exact answer. Negative square root of 2 minus square root of 2, all divided by 2. And we have a match. Yes? Good. So you obviously won't have that benefit of being able to check, but just so you see that we got the exact version of that answer. Okie doke. And a couple more verifies. If you look at this one, do we see a double angle here and a double angle there? Yes? Okay. So when I'm making my choice for the 1 minus cosine 2 theta, I have no choice on the denominator. That's just 2 sine theta cosine theta. 1 minus. When I'm making my choice for the double angle, here's my thought process. If I use this one, my 1's will cancel. Do you see that? 1 minus, and then if I use this one, my 1 minus 1 will cancel. And that to me is good, because then I won't have a binomial up top. So I'm going to use that one, 1 minus 2 sine squared. My 1 minus 1 cancels, and then my minus the negative 2 sine squared up top leaves just 2 sine squared over 2 sine theta cosine theta. And then your 2's cancel. Your sine theta cancels with one of the sines from the top, leaving just sine theta over cosine theta, which is just tan theta. That choice for cosine of 2 theta is something that you, just with practice, will get better at. You'll get better at it by making the wrong choice, unfortunately, doing a lot of crazy work, and then seeing what the right choice was, and then you'll slowly get a knack for what to look out for. And I'm just telling you in advance, I was looking out for hoping that those ones would cancel. Okay? And then over here we have a half-angle formula for tangent on our left. So I'm going to start there. And because I do have, oh, and I have to actually talk about this. There are 3 formulas for the half-angle of tangent. 1, 2, 3. So we have another choice to be made here. First of all, as far as the plus or minus, I have no guidance as to what to choose. So I'm going to probably stay away from that because I don't know whether it would be plus or minus. But look at these 2 examples and look at where we're trying to go and see if either of them looks better to you. I think I actually did this both ways using either or, so I don't think it matters. But Stephen, what do you think? And what's your reason for choosing that version of this? Right. If I use this with a monomial as my denominator, I can split it up into 1 over sine theta alpha and negative cosine over sine. So I'll use that one. Then I'll split it up, 1 over sine theta sine alpha minus cosine alpha over sine alpha. 1 over sine is cosecant, and cosine over sine is cotangent, and you're done. So your homework for tonight is going to be what it was supposed to be last time.